Okay, so in this video we will focus on the IHC cell detection app. This app you would use if you want to quantify cells in your bright field immunohistochemistry stain, like this one. So as an example here we use breast tissue stained with HER2. And let's begin. So we open the image analysis side panel here on the left-hand side. And here we work from top to bottom. So the first step is to open up the App Center and then select our app that we want to use. So we'll use the IHC cell detection app, focus of this video. And then here in the configuration settings section, this section here looks different every time, depending on what app you selected. So these are all the parameters that you can select or that you can use to tune or to affect how the app operates, what it does, how it works. And then here in the batch export settings section, so this section it does not depend on the app, so this is constant. It looks always the same. And yeah, then here these buttons start and analysis. So why don't we just do that? So I'm going to click field of view. That means it will analyze the currently visible field of view. And instead, if I clicked, so if I'm going to remove my annotations, if I clicked ROI, means I can first create regions of interest. So just here 2 arbitrary ones. I'm going to select them. So I press the Control key on the keyboard, or I could also just use the selection rectangle tool, or click here and say select all annotations. So whatever way I choose now, 2 annotations are selected. So I see that here. And now if I click ROI, it will then analyze only these regions here. Finally, if I click slide, I think that's obvious, then it will analyze the entire whole slide image. And this button here will always analyze the same region as before, just applying the new parameters. Okay. Yeah, you can see here, it will always show us some diagrams here where we get a sense of the positivities ratio of the cells per square millimeter. And here we have the scatter plot where we can investigate different attributes. Right, but let's now go to the start and learn how this app works and what all these controls do. Yeah, so the first section here is the tissue detection. So like many apps in MIKAIA, this one offers, like if the tissue class here in green, and we zoom out a little bit, we see the outlines. So if this has not yet been detected, because the tissue detection app is also available as a separate app here. So if that has not yet been run, it can be run implicitly at the start of the cell analysis here by this app, if it's checked. And I recommend to always do that, at least when you work with whole slide images. So then, because then especially if you analyze the entire slide, that means the analysis will be constrained to only the foreground, and all the background areas can be skipped. Okay, so then in the main section here, the first step is to select the AI model. So two AI models are available. The generalist, they're both generalist cell AIs. This one here is a smaller model, also means it's a faster model. It's been trained by us, so it's based on CellPost, but it's been trained on a custom data set comprised of different nuclear markers, membranous markers, cytoplasmic markers from different marker types, different organs. So the goal here really to have a generalist kind of universal IHC cell AI. So always try this one first. If this one does not work to your satisfaction, then try to fall back to this XXL AI model here. Again, it's a universal model, but this one's based on a foundation model, so the AI is a lot bigger. It generalizes a lot better to data that's not been present in our data set, in our training set. But it comes at a cost, so this model is way bigger, and that means it's approximately 5 times slower and also takes longer to load. So for that reason, I'd always recommend trying with a small one first, and then only fall back to the bigger one if required. So the next section is the stain. So it's important that the stain unmixing matrix here, basically this is what this affects, how the stain is deconvolved, matches your slide. So you can see here we have a HDub stain, and we are using our preset here. If you have a different stain, you can create your custom stain unmixing matrix and then save it, and then it will be available here. But that's out of scope for this beginner's video for this app. Okay, yeah, and why is the stain unmixing important? Because this is how the app works. So essentially, it will unmix the stains here, and this is how the hematoxylin component works, and this looks like, and this is how the dub component looks like. So these two images will be fed separately to the AI model, which will predict the cell outlines, and then the app will measure both the hematoxylin intensity and the dub intensity individually for each cell. And then based on the dub intensity, decide if the cell is positive or negative. So for that reason, the stain unmixing matrix here is important. And then in the next row here, we can configure a minimum and maximum cell size. I would recommend at the start to not be too restrictive here, use a big window, because essentially this will filter cells out. And I think in the beginning, you don't want to filter too much. You want to see what the AI picks up. And then subsequently, you can filter out too small or too big cells. Okay, so we'll skip over this row here for a second and continue here with the negative section. By default, you want to enable that negative cells are visible. And then also again, here you can require a minimum intensity for the counter stain, also maximum. Again, I would not be too restrictive in the beginning and just use the full window. Okay, and then lastly in this section here, this is concerned with deciding when is a cell considered positive. So essentially here what we need to do is provide a threshold. So that means here any cell with a mean dub intensity equal or larger to 45 and equal or larger smaller to this number here, 255, will be considered positive. But now the problem is, of course, how do you know that threshold? You can use trial and error. So if we look at here at a cell, click on it, and then here these attributes here are always related to the currently selected cell. So we can see here the hematoxylin intensity that's been measured and the dub intensity, so in a range from 0 to 255. That gives us a sense. But instead of starting with trial and error, what I would recommend is to use the automatic mode. And the automatic mode, if we use this for a second, in the automatic mode, you can see now here how cells initially are assigned to the pending class, and then only in the end they will be classified. Because what happens is, if automatic mode is enabled, what happens is that first the app will will do the measurements and then collect the dub intensities across the entire set of cells, and then only in the end it will select a threshold that optimally divides the set of cells into two subsets, into negative and positive cells. And I think this should also explain why it's important, if you use the automatic mode, that you analyze a region that contains both positive and negative cells. Otherwise, this the best cutoff, the best threshold cannot be found. And then it's reported here. So for one, we can see it in the scatter plot. By default, on the x-axis, it shows the dub intensity. And here, this vertical dashed line is now the cutoff, the threshold that was selected. So it's here somewhere around 30. But you can also see it here in this table here. So it's 33. And now, in fact, we can click here in the scatter plot on a cell that's just above the threshold. So this is just barely positive. And then on the other hand, this one's barely negative. So we can visually check if we agree or not. And then if we disagree, now we know 33 was our automatically found threshold, so when we can adjust it in one side towards or the other side. Good. Now let's quickly check how to get rid of some of these false detections here that are, I think, way too small. So we can click here on any of these objects and then get a sense for their size. So this, for instance, is 6.6 square microns. This one's 12, 11. What we could also do is check here, use the scatter plot, filter by area, and then maybe zoom in a little bit on the lower end, click on a point, and then the viewer will jump to that particular cell. Here we go. Sometimes these points are a little bit too small, so we just increase them here like this. Okay, so now we can jump to those, and yeah, I think I'm going to go with a minimum, maybe around 15 square microns for the cell detection. Also here for the positive, it could be the same number. And now if I rerun, then those cells smaller than that, are those detections that are not really cells, they will just be discarded. But if I want to check what has been discarded, then it's actually, I can here go into the advanced section and enable verbose annotations, or enable this option. And now if I rerun my analysis, you can see here how it now creates a class with false positives. So here too small. I could also have too big or too dark. Here in the false positive section here, I can set some additional options. So I can require that so M minus means the negative marker, so the counter stain, M plus is the marker stain. So I can say that if both of these are really small, or if one of them is small and the other one's bigger than some threshold, then these would be counted as false positives, and then they show up here. Or for instance, here, if a cell is too black, for instance, when analyzing lung tissue, where tar is always a problem, I could look at the blackness value of a cell and then filter that. So different options, but in any case, so when the verbose annotations mode is enabled, then they are still discarded, so not assigned to the negative or positive class, but I can check here which objects have been discarded. And then in the end, when I'm confident with my settings, I should then disable this again. Okay. Yeah, now another important thing here is that so far we have based our DAP expressions for the cells on the average that's been measured across the entire cell. But clearly, in this stain, only the membrane is expected to be positive and the nucleus is expected to remain negative. So the nucleus should not be counted. So one option that we have is to base or to compute our DAP expression not based on the average in the entire cell, but we could say we only want to measure the darkest or the most intensely stained, let's say 10 or 20 or 30%. So let's repeat this. And now what we, in fact, I don't want to use the automatic mode. I want to use this manual mode. Yeah, so now what we see is that most of them here will now be positive, whereas if we base it on the entire cell, you can see how many of them remain negative. So this is a behavior that we then expect. Instead of just picking up the darkest sub-area of each cell, we could also take another approach and use the new subcellular mode of this app. So here we can say that we want to interpret the contour that we get from the AI as the cell's outer contour, so as the membrane contour, as the cell contour. And then based on that, shrink it to obtain an estimate of the nucleus. So maybe we shrink it by 2 microns. Could also, on top of that, expand our contours a little bit where space. So if there's another cell nearby, then this will not take effect. Okay, so now when we do that, each cell will essentially be comprised of 2 compartments, of 2 zones, an inner zone and an outer zone. So the inner zone is the nucleus and the outer zone is the cytoplasmic membrane, or only the membrane, depending on how much we shrink. And then, so if that's the case, then we have an additional option here in the positivity section, and here we can select, now should we base our decision, is the cell positive or negative, based on the expression in the nucleus or in the cytoplasmic membrane. So here we want this option. So I'm going to repeat my analysis. So now, as explained, each cell is comprised of 2 compartments. If I click, for instance, on this one here and look at all the attributes, so now we see here we have a DAP measurement for the cytoplasm, which is 43, and then one for the nucleus, which is way lower, 25. That's what we expect here in the cell. So the intensity, the average in the entire cell was, oh no, actually, no, that's wrong. So here, this is the threshold, 32, that we set up. Yeah, but you can see the average would be probably way too low due to this unstained nucleus. So now this 43.4 that we've measured here for the outer contour is used. And here, then again, here, if we look at the negative cell here, what we expect is that the DAP intensity in the cytoplasmic nucleus is close to the same. So here we don't see a difference. Okay. Yeah, so this should be helpful. I think now we got the basics covered. Let's look at grading. So sometimes it's important or not sufficient to only classify into negative and positive, but maybe you want to subclassify into weak positive, medium positive, or strong positive. And for that, you would enable the grading. You do that here, and then set ratios. So this is 100%. So and this 100% relates or is relative to this green region here. So 0%, this number would be the threshold, would be 32, which is now our minimum intensity that we require the cell to be positive. Yeah, I hope that's clear. Okay, so now if I repeat this, yeah, I think that's more or less what we expect. Most of our cells are now assigned into the weak positive class. Maybe if I decrease my threshold here a little bit, like this, you can see some cells also in the moderate or in the strong class. But here, I think in our case, this is not a very intense stain, so I think more or less what we expect. Enabling grading is also a prerequisite if you need to know the H-score. So the H-score is essentially a formula that takes into account the ratio of weak to moderate to strong positive cells. Yeah, so if you need H-score, enable grading. Okay. Let's look at the hotspots. So we're going to skip over. So we've briefly touched the false positive filters here, but won't go into detail. We will also skip over the divide by regions of interest. So this one here is important if you want to take different measurements in different regions. For instance, compare these kinds of statistics that you get from this analysis inside the tumor versus outside the tumor, or inside versus nearby versus outside, or use the AI author app to first identify different tissue types and then compare IHC cell statistics in those different tissue types. All that's possible divide by our eyes feature, but we'll keep that to a different video. Yeah, so let's briefly look at the post-processing options. These are easy to explain. So the search hotspots mode, you can just enable it and then say or select the diameter of your hotspots that you want to find. And then you have two options, or you have three options. You can say you want the top, I don't know, top two or top three, top one hotspot. So the radius or the field of view, 500 microns diameter that contains most positive cells. Alternatively, you could say you want all the hotspots that contain at least this number of cells, and then if you're interested in the number of hotspots, or you can combine both constraints and say you want the top, I don't know, top two hotspots, but a hotspot has to have at least, I don't know, at least 20 cells. Okay, I think this should be straightforward. If we run an analysis quickly, right. So now it found two hotspots here. This one contains 1,500 something positive cells here, and this one 1,200. Yeah, so enabling this feature doesn't really hurt. If you export your results, your statistics into a CSV, the information on hotspots will be contained. Yeah. Okay. Now we look at the other option, the other post-processing option, group into clusters. So what this does is it will group all the nearby positive cells into a cluster. So we give a maximum radius. So it means if there is looking or focusing in on a positive cell, if there's another positive cell within this radius, then these two cells will be grouped into a cluster. Let's just try it out. I don't know if 30 microns is a good threshold. Yeah, okay. This makes sense here. So here all have been assigned into the same cluster. We can repeat it here. Here what we see is a lot of very small clusters, clusters with only less than 5 cells. So we could require that a cluster has to have at least 10 cells.